Good afternoon, Doctor. My name is Kheng, metric number U2104524. We are from Group 11 and the application we choose for this assignment is Mechanical Ventilator.
My name is Wilson, metric number 22004691.
My name is Hui Ping and my metric number is 22004631.
My name is Ooi Ow Wen and my metric number is 22004630.
In our problem, we need to determine the pressure that must be provided by the mechanical ventilators to achieve this specific flow rate, given that the ventilator supplies pumping power of 258.1 kilowatt per hour annually and operate at the efficiency of 90%. The ventilator also delivers oxygen at the inspiration flow rate of 50 liters per minute, and the density of air is 1.2 kg per meter cube.
Now we'll be talking about the methodology part. There are several theories and principles of fluid mechanics and transport processes being applied and implemented in the operation and usage of a ventilator. First and foremost is the pressure and flow relationship. The Bernoulli principle plays a critical role in the functioning of ventilators, particularly in the processes of air and gas flow management. According to Bernoulli's principle, in a steady flow of an incompressible fluid, an increase in the fluid's velocity results in a decrease in its pressure. Besides, the principle of conservation of mass is implemented in the operation of a ventilator. In ventilators, the principle of conservation of mass and volume flow rate control is paramount to ensure that the correct amount of air and oxygen is delivered to a patient's lungs. Last but not least, ventilators apply the principle of mechanical energy and associated energy equation. Mechanical energy is the form of energy that can be converted to mechanical work completely and directly by an ideal mechanical device, such as an ideal turbine. It does not change during flow if its pressure, density, velocity, and elevation remain constant. The concept of pump efficiency is applied expressing the effectiveness of the conversion process between the mechanical work supplied or extracted and the mechanical energy of the fluid.
Now I will discuss the result. The assumptions we made are the airflow is steady and incompressible, the elevations level of the mechanical ventilator and the tube connector on the patient's mouth remain constant, the tube connector diameter at the inlet and the outlet remain constant, and the pressure at the patient mouth is assumed to be nearly the same as the atmospheric pressure. The total mechanical power loss is negligible. Then, the analysis shows that the airflow rate and the density are constant over time. The elevation difference is negligible. No turbine is involved in this system. Proceeding to the calculation, firstly we will determine the pressure at the mouth, which is P2. Then we will convert the flow rate to SI unit and determine the mass flow rate of the air. Next, we will calculate the useful pumping power of the ventilator. Finally, after understanding the Bernoulli equations, the energy equation can be applied to get the pressure provided by the mechanical ventilator, which is 69.17 kPa.
I will be presenting about the discussions of our problem statements. So based on the results, it shows that the pump can provide an increase of 37.41% of pressure at the outlet. So what are the ways to further increase the efficiencies at the same time maintaining the safety of the mechanical ventilators? So first of all, we should increase the mechanical power output of the pump. Since the faster the rotation speed of the pump, the faster the rate of shaft work done per unit time. And also, we can minimize the minor loss by using a compressible bellow. Furthermore, we should increase the volume flow rate under safe circumstances to achieve the minimum required inspiratory pressures at lower initial pressures, therefore increase the overall efficiencies of the ventilators. So at the same time, we should also maintain the safety of the ventilator, so the pump shall always provide minimal adequate power to maintain the positive and expiratory pressures, PEP, to the patients, and also avoid negative and expiratory pressure, NEEP, of the patients.
In conclusion, medical ventilator use a lot of application of fluid mechanics, and we have determined that the ventilator can increase the pressure at the outlet by 37.41%, thereby providing effective ventilation support with relatively low initial pressure. We can also increase mechanical power output by several ways, such as increasing rotational speed of the pump or using compressible bellows to reduce minor losses and enhance efficiency. Overall, these optimizations and considerations are essential for ensuring that the mechanical ventilators provide safe, efficient, and reliable respiratory support to patients.